Starting. All right, so you've done some SciPad pre-learning. Hopefully that has helped you kind of get some terminology and some information down, and hopefully you might have now realized how your science teachers have been lying to you for many, many years. So, something to keep in mind when we are thinking about electron configuration. This is the model you guys are used to seeing, which is the solar system model. And we've told you that the electron configuration is 2882 for a very, very long time. People often ask what happens after calcium, because if you add up 2, 8, 8, and 2, that's 20, and that's calcium. And I've always told my students, don't worry about it. If you want to know what happens, you're going to take level 3 chemistry. And congratulations, you guys are now in level 3 chemistry, so you get to know the real story and not the lies we've been telling you for years and years and years. This model is actually not correct. What actually is correct is this model over here. So instead of having the electrons orbiting around the nucleus like a solar system, what actually is happening is that the electrons exist statistically in a set location known as a cloud. This electron, and I'll try to highlight to make it bigger. You see how the electron's like popping around? That is realistically what's happening with the electrons. It is not going in a nice little solar system. Wow, I've been lying. It's popping around, and what we have is the electron cloud, and that is an area that we expect this electron to exist. On top of that, not only do we have shells, but we have subshells. So there's different shapes that these likelihood of where you're going to find these electrons are going to be. So let me pass out some notes, and let's talk about the truth. The truth. All of the lies that I've been giving to you guys all these years. No longer. I'm sorry, we've been teaching the wrong thing for many years.
I see the one. We see all. The truth is
the truth. The truth.
So relative.
Okay. So sorry we've lied to you for so long. Okay. So, as I was saying, these electrons exist in a shell, in a cloud, and it will exist somewhere in that shape. It'll bounce around and pop around from various locations, but statistically speaking, it should be in a set area. What we've been previously telling you, which is incorrect, keep saying that, just so you guys know that, is before what we've been saying is that say for example, you take nitrogen. We have nitrogen has the, atomic number of 2. I'm trying to remember where nitrogen is. Let me just find it. I want to say 7. Yes. Okay. So, we've been telling you that nitrogen has 7 protons, which is true. Generally 7 neutrons, depending on its isomer. And then we've told you that electrons exist as 2, 8, 8, 2. So that's what we've been telling you, right? That is actually not correct. In fact, what is happening is we have nitrogen and we have our nucleus of protons and neutrons. Whoopsie, what am I doing? 7. And then what we have around it are clouds of where you're likely to find those electrons. They take different types of shape. So the first shape you have in that first orbital, oopsie, that's not what I wanted. I wanted this one, is you have this S shape. That is a sphere. And we have that in the first subshell. The first subshell only has the S subshell. So if we had that first 2 electrons, they're going to be existing in the S, I should say 1s2. So 1 indicating that it's in the first shell, S is the suborbital, and you have 2 electrons in that suborbital. So that is the shape it's going to take. Think of it as a 3-dimensional shape. It is like a sphere, and you have the 2 electrons popping around in that location, and they'll just be likely found in somewhere in that area. All right? Then the next 2 electrons are now in the second shell, which is 2. And once again, with 2, you have an S shape. So it's going to be slightly further out, and the reason why it's important for us to talk about this is because it will come up in the periodic table trends. It is also a sphere shape, and it is popping around in that area instead. So that's likely where you're going to find it. All right, so that takes care of 2s2, so that's another 2 electrons. If we're thinking about nitrogen, there's another 3 electrons that we need to think about because we're going up to 7, which is 5 in the second shell. Now we start getting into the p suborbital. So this has a different shape. It's kind of like a dumbbell, and you have to think about it as 3-dimensional shape as well. It's not, even though 2D is what I'm showing on the piece of paper, it's actually 3D in real life. So you have stuff that's going against the x orbital, and you have basically, like I said, a dumbbell like that going horizontally. You have one that's going up like that, and you also have one that's going in the y orientation as well. So you have 3 suborbitals with the p shell. So what you would see then in this case is you'd have like a dumbbell going this way, you'd have a dumbbell going this way, and you'd have a dumbbell going that way, because you got to think in 3 dimensions. And those electrons are popping around in their assigned suborbital. Are we okay with that so far? No, we're not. Okay, let me find the PhET software to P, what is that, 3 now. So now we're starting to annotate in more details. Before, you guys would have said this as 2 and 5. 2, 5. Now we're getting more specific. I think PhET probably has a simulation to show you this. Let me just see. Hopefully it does. I thought I saw something that's building an atom that shapes. Ah, very strange. I thought you would have one. Oh, here it is. Nope, that's molecular shape still. Well, that's annoying. Could have swore they had one. Just double checking not being done. Let me just show you guys subshell shapes. So I have this on the image for you guys, but I'll just blow it up a little bit bigger so you guys can see it. Are you in video? Can I just have an image? Select the digital one. Why are you being weird with the login? I just want to see that picture. Speaking of pain in the butt. I might switch to my other notes while the time being. I'll just zoom up. Okay. So some things to keep in mind is you have these suborbitals. So basically you still have the shells that we've been talking about, but we're just getting more specific on their shapes. So first shell that you have is the S suborbital. That is just a spherical shape, and it holds, each of these little orbitals hold 2 electrons. So when we talk about the first shell only has the S shape. So just that one. Now, since we only can hold 2 electrons, that then means that the first shell only holds 2. So that is true. The next shell has the S orbital and the P orbital. So the second shell has both S and P. S holds 2, P 2, 4, 6. So that's 2, that's 6. You add 2 and 6 together, that gets you the 8. So that's how the 2, 8 has come from. So the second shell has an S1 and it has the P1 as well. So you see how I've drawn the second shell here with the red line to show the S1, and I've drawn the little dumbbells to show the P orbitals. So those together make the make the second orbital. Then the next one here is our D. You have 2, 4, 6, 8, 10. So there's 10 in that one that I can hold. And then you also have the F, which is 2, 4, 6, 8, 10, 12, 14. 2, 4, 6, 8, 10, 12, 14. Yeah. So that is the number of electrons it can hold. So when you actually go to the third shell, before we told you that it only holds up to 8, in reality, it has 2, 6, and 10 because it has the s, p, and d suborbital. So really, it can hold 18. We've been lying to you and telling you it's only holding 8. And I'll explain to you how that is the case and where that has come from. But the important thing to take away from this is that, there we go, finally it's loaded. You have all these different orbital subtypes, and they have different shapes, and in those shapes is where you're likely to find the electron. So we're just trying to zoom in a bit more and get a little bit more clarity on what the orbitals actually look like. So like I said, they don't look like a solar system like this. What they instead look like is that. And you can see why we did not teach this to you in year 9 and 10, because it gets yucky. So here is something else to keep in mind when you're looking at these suborbitals. As you're going up electron shell-wise, they are further and further away from the nucleus, and that is going to have different energy levels. The other thing to keep in mind is that these shapes also have different energy levels as well. As we get more complicated, the more energy is in those ones. When it comes to how the electrons are going to fill the atom, it wants to fill at the lowest state possible and then the next one up. So just like we were talking about previously with the 288 rule and how it's filling up, it's just basically stating what is the lowest possible way it's filling up first, and then it's moving on to the next one. So here's the little nasty thing that unfortunately you guys have to memorize. It's not actually too hard to draw because it's pretty, I would say, logical. So first subshell has 2. Second shell has the S and the P. P holds up to 6, so total we're still at 2 and we're still at 8, just like you guys have been doing previously. Third subshell is 3S2, 3P6, and 3D10. And then the next one is the fourth, S2, 4, 10, and then F, what did I say? 14. And then, yeah, the 5. So you just write it down in this order. And like I said, it's a lot of work for an achieve point. You don't have to explain how this works at all. We'll go up to 6. So you might have actually seen this when you guys have been Googling. All right, are we okay with that?
Sorry, guys. That's 5. So the 5 set.
Oh, that's supposed to be an S. Thank you. So when you're trying to fill things in quickly. All right, are we okay with that? All right, let me show you guys how you've been filling this in the past. Hopefully it'll help kind of cement what we're thinking about. So when we're trying to fill things from lowest to highest, you fill in the first shell first. You then start filling the 2S one like that. You then start filling in the 2P and then to the 3S, and then you start going that way. So this is kind of the angle you're looking at.
But what does the numbers in the front mean?
So the numbers in the front tell you the shell. So first shell, second shell, third shell, fourth shell, fifth shell, sixth shell. Okay? So first shell, you fill in the 2. Second shell, you'd fill in 2 for that S1. And then once you finish that, you go to the 2P6.
So if there's more than...
Yeah, so if it's more, then you just go to the next one. So if I was talking about nitrogen, 2 goes in there, 2 goes in there, and then 3 goes in here into the P shell. Okay? Now, if I have over 6, I'd go to the 3S. All right? Then, if you fill in the 3S2, you go into 3P6.
You just move them.
And then once you fill in 3P6, you go on to 4S2. This is where you guys stopped. So if you mathematically think about this, this is 2, that's 8, that's 8, that's 2. And then we told you not to worry. The reason we told you not to worry is because after you get to this point, you have to go back to the third shell. Because that is, this 3D10 is a lower energy level than the 5S2. So that's why we're going back here. So this is the nasty thing about electron configuration, which is why we didn't tell you the whole story. So that's the 2, that's the 8, that's the 8, that's the 2, and now that we're past calcium, we're going to go back. Because that 3D is actually a lower energy level than the 5S. In fact, that 3D is actually a lower energy level than the 4p.
But doesn't it make sense for it to be the lower energy level because it's only 3 shells?
So this one is more complicated, but it's lower. This one is less complicated, but further away. So you're trying to compromise those two things: distance from the nucleus versus complexity of the shape. So that's why instead of going from 3p6 to 3pd, from the 3p to the 3d, because you think logically that's in the third shell, we should go that way. It goes, no, we're going to jump up a shell because the 4s is a simpler shape than the 3d. So even though it's further away, it's a simpler shape, so that's why it's getting filled first, and then it backtracks to fill that. Because when you compare it against this one and this one, or this one and this one has the lower energy level. So they don't give you this on the exam. You do have to write it down, and then you just fill it in as you go. Are we okay with that? That's a pretty nasty way to show you guys that. I'm sorry. It also follows, like I said, trends in the periodic table. So if you look at the patterns and how the periodic table goes, you have the 1s, now you're starting the 2s, you fill in the 2p, then you fill in the 3s, that's 2, then you fill in the 3p, then you fill in the 4s, that's 2, then you fill in the 3d, then you fill in the 4p, then you go back to the 5s, then you fill in the 4d, then you fill in the 5p. So it's showing the same pattern that you're saying here. Neither of that will be given to you on the exam, so you do have to have this at least known. Are we okay with that? I feel like I didn't explain that terribly well. All right, let's see some examples before we go, and let me explain to you guys some outliers with the rules. So, I know, you guys are going to hate this for a while. Okay, let's say, for example, we are thinking about Tn, which I need to find on the periodic table. Don't think that's 10. Tn periodic table. Is it 10? Oh, it's titanium. Nice, just like the song. All right, let's look at titanium as the example. Titanium has the atomic number of 22. So if I was to do the electron configuration of titanium, I would start here, and we're working our way up to 22. So 1s2, 2s2, that gets me up to 4, 2p6, that gets me up to 10, 3s2, gets me up to 12, 3p6, that gets me up to 18. Then we go 4s2, that gets me up to 20, and then now I'm backtracking here, and I'm going 3d2.
3d6.
3d6. Oh, p. Thank you. And that's how you do that. You can rearrange these so it's all in order, but it's not going to hurt you if you do it like that. Something to keep in mind as well is there are a couple of exceptions to the rules, and there's also some things to think about when you're dealing with ions. Are we okay? Keep going. All right. First exception to the rule is chromium, which is Cr. It has the atomic number of 24. Now, if you were to fill in chromium, you would think, I got to fill all these guys in, and this one is 24, so this one's 22, so I'd be changing this number to a 4. That's what you guys would think. That's what you guys would think would happen. What actually happens is, because it's in a unique situation, atomically speaking, if you notice the D shell has 10, and you could have a half full shell, which would be 5. So what happens is this actually becomes a 1, and the electron goes over here and becomes a 5. Because it's more stable to have a half full shell than to have this full shell and then this as like one empty shell. The thing you have to keep in mind when it comes to how the electrons distribute in the suborbitals, this is what they're talking about with the Hund's rule. So this is the D suborbital. One electron will go into the suborbital before it starts doubling up, like that. So this is just referring to each electron. So in this case, it's actually more stable for it to have the half-filled D shell. So that's what it's going to do instead of having 4 and 2. It's just a weird exception to the rule. You got to watch out for that one. Are you okay with that so far? The other thing that I should keep in mind, and I forgot to mention this in the previous example, is you can shorthand this by annotating where the noble gas is on the periodic table. So if we're thinking about the noble gas, and we're thinking about argon on the periodic table, let me just find a periodic table for you guys. So argon's over here, which would be here on this periodic table. So argon's over here. So what you can do as a shorthand is, say for example, titanium, which is over here, you could write argon in brackets, and then you can write the remaining things that are missing. So argon is just basically stating you're keeping this bit of the notation summarized here, and then you just add the next two. Like that. So argon here is representing this bit here. So if you want, you can shorthand it that way too. It adds up to the same thing. They both mean the same thing. So these are two different ways you can answer it. Don't stress too much about this. This is only an achieve point. It's a lot of work for an achieve point. All right, keep going. All right, next one I want to talk about is copper. See you. Copper is 29 on the periodic table. It also has a weird rule. What you would think, again, is that you would have 2s here, and then you'd have a 9 over here, because you think that's how we add up to copper for 29. Again, it does the same thing that chromium does. It takes one of the electrons off of the 4s suborbital and puts it onto the 3d, so that way you can have a full d orbital there. So let me write it down. So this is what you think would happen, right? Because that's how you'd add up to 29. What actually happens is this becomes a 1, and it gives the electron over here, and that becomes a 10. It's more stable to have a full D shell. So some weird exceptions to the rule. All right. The other thing to keep in mind is that they will ask you questions about the ions. So just remember that you need to adjust the ion number, number of electrons based on the new ion. So for example, if you're forming a positive ion, then you've lost electrons. If you're forming a negative ion, you have extra electrons. So just be mindful of how you'd adjust the electron configuration based off of the addition or subtraction of electrons. You do have to be careful of transition ions because they will remove from the outermost shell, not the last fill shell. So for example, if I have the copper 2 plus ion, I need to remove 2 electrons, correct? Everyone agree with me? This was the shell you filled last, but this is the shell that's furthest away. So when it takes the 2 electrons away, it's going to first take away from the 4s, and then it'll take away from the 3d. And so it's taken 1, 2, so now that's 9. So that's something to just watch out for. It's the same thing. If I was forming titanium as the ion and it had a Ti2 plus like that, this was the last filled shell. And if you were filling it in order based on following this sheet, you would have been like, oh, I'm going to stop here and then not add these 2 electrons here. Whereas that is incorrect. You need to take it from the furthest one, which is that guy here. So that guy would come off, that guy would stay. So something else to watch. With ions, personally, what I do is I do the atom, do the electron configuration, and then take the electrons off. So that way I don't accidentally take it off the wrong shell.
Well, if it's 3 plus, what do you do?
If it was 3 plus, then I take the 2 off here and then 1 off there.
So it'd be...
Yeah. So that's what I was talking about. With transition ions, you have to be careful because they have that furthest shell. You have to take it from the furthest shell first and then take it. Whereas if you were trying to fill this and you were doing this method here, you would go, oh, 1s2, 2s2, 2p2, 3s2, 3p6, and then you would have done 4s2, and then I'm not going to do my last 2 electrons. That's how you would fill it. But then you'd be like, oh, wait, there's a mistake because that's actually the furthest shell. So the 2 electrons should actually be here because that's the shell that it's going to take it off of. So you have to be careful of that. All right? It's a lot of work for an achieve point. All right. But like I said, the only thing you're going to have to do on the assessment is not any of the stuff that the SciPad's doing. You're going to be doing the, where to go? Like I said, look on No Brain Too Small, because you don't actually have to do anything. Like, there's some really complicated stuff in the SciPad. You don't have to do it that way. Find it. I did put some past exam questions onto Google Classroom. So this is basically what you've been doing on the exam, is just this stuff here. A lot of work for an achieve point. They do give the periodic table. So you will know atomic number, and then if you can just write this down, then you're fine. And then just remember what happens to transition.